Number 48, professional application. A 5.5 kilogram bowling ball moving at 9 meters per second collides with a 0.85 kilogram bowling pin, which is scattered at an angle of 85 degrees to the initial direction of the bowling ball and with a speed of 15 meters per second. Letter A, calculate the final velocity, magnitude and direction of the bowling ball. All right, so here's our basic setup. Here's the bowling ball. It's initially traveling at 9 meters per second. It has a mass of 5.5 kilograms. And the bowling pin is initially stationary, has a mass of 0.850 kilograms. After the bowling ball makes contact with the bowling pin here, the bowling pin, as it told us in the problem, is going to be scattered at an angle of 85 degrees relative to the horizontal component, all right, of the bowling ball. So here's my 85 degrees, all right? This vector right here in red basically represents V2A. Hold on one second, I realized I got 2's in here. Let me just erase them, 1 second. Here's a 2 and here's a 2. Sorry about that. We have V2A, and this vector here has a value of 15 meters per second. And we are looking then for the final velocity of A, right? The final velocity, not of A, but the final velocity of the bowling ball of object number 1, okay? Maybe the bowling ball's, scattered here, has a certain angle. Maybe it hits it and it goes this way. I don't really know. I do have an idea, but let's just pretend I have no idea where it's going to go. We'll try to do this without even knowing what the picture might look like. All right. We're going to use, so first let's start with what type of a collision might this be. Well, it sounds to me like it might be an elastic collision. I'm going to use conservation of momentum to help me out. All right. Conservation of momentum says that the momentum before must equal the momentum after. Now, once you start getting vectors, right, in two planes, both the x and the y plane, you want to start breaking up your momentums into x and y components, just like you've done for kinematics, just like you've done for forces. So now basically I'm going to add a little x down here, all right? And I would also create another equation that the momentum before the collision in the y direction should equal the momentum after the collision in the y direction. Okay, so now let's expand these terms. Remember, it's elastic, so I should have 2 items before and 2 items after. So the total momentum before the collision will be a function of I'll just write the momentum of the first object before the collision in the x direction plus the momentum of the second object before the collision in the x direction. That should equal the momentum of the first object after the collision in the x direction, plus the momentum of the second object after the collision in that x direction. Same thing, I'm not going to do it just to save space, but you would expand this y equation in the same exact way, just substituting out these x's for y's. Okay, now, as soon as we start having to deal with x and y components, what do we like to do? We like to create our component table, right? It helps us organize our thoughts. So let's create the component table. I'm going to try to squeeze it down here on the bottom left. All right, we'll do X. Now let me give myself a little more room. I'm going to have Y components here. All right. I have 4, vectors here, right? 4 potential vectors. So I'm going to talk about each of them and plug them into the table. Or actually, you know what I really should be thinking about? I should be thinking about the overall vectors. Forget about the X components for right now, but I can be thinking about the overall vectors. So let me plug in, you know what? Already I can see I'm going to run tight on room. Just move this over a little bit. Okay, so let's take a look. We got 4 different items, right? Where you got the momentum of the first object before the collision, we have the momentum of the second object before the collision, then we have the momentum of the first object after, and the momentum of the second object after. Okay, so let's see, let's start plugging in some of these x values, and maybe we know them already or whatnot. So if we had to think about the ball, right, before the collision, what is it doing? The ball's moving horizontally. Okay, does it have any y component? No, right? It's not moving up or down at all. It's moving purely horizontally. So we know that the y component here should be 0. What I'm going to do too is I'm going to add a couple of lines here just so we can separate the numbers. Okay, 1 second. Okay, 1 more. All right. So now, and the x component now of this first a momentum, right, is purely horizontal. So I know, this x component will be exactly, P1b, okay? P1b. Whatever the momentum is, okay? Let's now look at P2b. Remember, before the ball hits the pin here, what is the pin doing? Well, it's not moving at all, right? There's no motion. So therefore, what's its momentum? Both in the x and the y, it's both 0 and 0. Okay, let's now break up the momentum of the first object after the collision. So remember, that's the black ball, and we don't know if it's going to be at this angle, right? It's going to have another angle to it, right? All with respect to that x-axis. We don't know where it's going to be. Not a big deal. But we do know, right, certain things about the x and the y components of that vector. Remember that x components, you should be noticing the pattern by now that cosine, right? If we're measuring the angle with reference to the x-axis, cosine correlates with x components and sine correlates with y. So now what I'm going to write in here is I'm going to write P1a, whatever that is, cosine of theta. That would be the x component. And I don't know what the angle is. And then the y component would be P1a times then the sine of theta. Okay, so those I don't know. And now what about P2a? Do we know the x and y components? Yeah, we can. Actually, we will be able to know these, right? Because we know the angles and so on and so forth. And we do know the V2a overall. But we still have to break it up into its x and y components. Okay, so that means that this would be P2a cosine of, I'm going to write 85 in already, okay, just so we don't confuse with all the thetas. And then this would be P2a cosine of sine. What am I talking about? Sine of 85. Okay, so now we have both sets of equations, right? We have our x components. We have our x components over here, right? And our y components over here. Okay? So what that means is now I can start plugging them into my equations up here. And then this expanded one, right? So let's do the x's. So P1b in the x was just P1b. Okay, so that's P1b. Plus P2b in the x direction was 0. So plus 0. Plus then P1a in the x was P1a cosine of theta. So let's plug that in. That should be an equal sign there. So P1a cosine of the angle. Great. And then, last but not least, it'll be P2a cosine of 85. So plus P2a cosine of 85. All right. So now let's simplify this. Okay. So I'm going to start breaking these up into x's and y's. All right. So let's do, so breaking this up would be m1 v1b, right? Should equal then, breaking this up, this should be m1 v1a, okay, times the cosine of the angle, plus then m2 v2a times the cosine of 85. Basically, remember, all I'm doing is I'm applying mv, realizing that momentum is the same as mv. So I'm just breaking up all of these momentums into their respective mass and velocity. So now remember, what we're after is we're trying to find the final velocity of the bowling ball, which is this variable right here. So now all I have to do is do some algebra to, to solve for it. Subtract this term on over to the left-hand side, and then divide everything. Well, actually, hold on one second, right? Two issues here. What are the two issues? Well, the two issues here are going to be that here I have one unknown. So let me not jump the gun. And here I have another unknown, right? So I actually cannot solve this yet. So let's stop here. And let's just conclude the video, actually. So guys, thanks for joining it. No, I'm kidding. All right, so we have to change gears, basically. So meaning that I know I have an equation here, but I have two unknowns. So let me just box these in, okay? So I can't solve this yet. So, but I'm thinking to myself, wait a minute, I also know my y's, right? I have my y components here. Maybe that can help me a little bit. So why don't we start plugging that stuff in, okay? Now, I could break this down just like I did. Let me actually put this in a different color. All right, just so we don't get confused with all the colors over here. So let's do, P, what do we got here? We got PBY is equal to PAY. All right, so this would be P1B in the Y plus P2B in the Y will equal P1A plus P2A. Okay, just go to our component table now and plug in the values. The value of the Y direction of the first is going to be 0, as we spoke about before. So this is 0 plus, that one's also 0, so that's 0. How about now P1A in the Y? Well, that's P1A sine of theta. So here we have P1A sine of theta, all right, plus P2A sine 85. P2A, okay, P2A sine of 85. So now this works out to be basically 0, right, is equal to this whole term. Why don't we break up the momentum now into mass and velocity? So let me give myself a little more room. So this would be 0 equals m1 v1a sine of theta. I don't know what happened to my theta there, but there it is. Plus then m2 v2a sine of 85. Okay. Now, what don't we know in this equation? Well, we don't know two things, right? We don't know this term, and we don't know theta. But guess what, ladies and gentlemen? Notice you have two equations now with two unknowns. So how do you go about and solve this? System of equations, right? Solve one for the other, and then plug it in, okay? I think it might be possibly easiest to solve, let's say, this equation for V1A and then plug in its result into this equation. Okay, there's a couple of ways you can do this though. So let's solve this equation right for V1A. All right, so let me take away the box. Let me just put the box around it now. So if I had to solve the equation for this, right, you're going to be subtracting this whole term on over to the left. So we would now get negative m2 v2a sine of 85. Right, will equal then m1 v1a sine of theta, okay? And then we have to subtract out the m1 sine theta, so that's fine. So why don't we do that? So we'd have v1a, and this whole side would then be divided by m1 sine of theta. Now, I'm going to take this and plug that result on in for my v1a here, okay? So let's do that. So now we have m1 v1b, okay, will be equal to now m1 multiplied now by brackets negative m2 v2a, oops, m2 v2a sine of 85, okay, all over m1 sine of theta, okay, times then cosine of theta, okay, plus this term, right? Plus m2 v2a cosine of 85. All right, so what is our unknown now in this problem? There's only one unknown here, right? It's just theta. Okay, so what I'm going to look to do now is I'm going to look to solve this equation for theta. So why don't we give that a shot? And I'm going to start doing the work. I'm just looking at where I'm going to start doing the work up here on the upper left. All right. So first thing I notice is that I have cosine over sine. And I know this to be the case, right? That I'll write it over down here, that tangent of theta is equal to sine over cosine. So therefore I know 1 over tangent would be cosine over sine. So I know that that's what I'm going to be working with here. Okay, so I'm going to combine that into just the tangent function. All right, let's do that. And then maybe there's some other items we might be able to cancel. I'm already noticing here's an M1, here's an M1, so they can cancel. Right, I'm going to basically be looking to simplify this now. Okay, so we got M1, V1B, okay, will equal now negative M2, V2A, times then times the sine of 85, times the sine of 85. Then remember, all over now, tangent. Okay, all over tan of theta. Plus m2 v2a cosine of 85. Okay, so we're after theta, right? So I just have to now solve this. I got to basically isolate this on one of the sides. Okay, so let's do that. What I'm going to do is subtract this term on over to the left. All right, so now we'll have m1 v1b minus m2 v2a cosine of 85 will then equal negative m2 v2a sine of 85 all over tan theta. And now basically what I can do is I can bring this denominator on up into the numerator on that side and bring this numerator, which because it's essentially over 1, into the denominator over there. And that'll basically get me tan of theta. And then I think we'll see where to go from there. So here's tangent of theta should equal now negative m2 v2a sine of 85 all over this whole term. Okay, m1 v1b minus m2 v2a cosine of 85. And this is, and now basically, okay, just to save a little space, I got to get rid of the tangent, right? So basically I have to do the inverse tan of the left and the inverse tangent of the right. Okay, so when I do that, let's just erase this over here. This would be theta. And I'm going to bring the theta over here. And the right-hand side now, it's going to be tan to the minus 1 of this whole thing. Okay, so this is my equation now. And this is what you would plug in now to your calculator to solve. The physics isn't bad. It's the math that's the killer here, right? I mean, you're talking about crazy substitutions and whatnot, and we got to do this so that we get, precise answers. But this would be the formula. So now all we have to do is plug in the values, okay, and then we're going to calculate. So let's plug in the values. We're going to do it over here on the right-hand side, all right? So I'm going to do tangent, so theta is equal to the inverse tan of, so negative m2. So remember, m2 is 0.850. I already can probably tell I might run out of some room. 0.850 multiplied then by v2a, which was 15. So that's 15. Multiplied then by sine of 85. Sine of 85. And that's now all going to be over this whole denominator, right? m1 v1b, so it's m1 v1b, so it's 5.5 times 9. All right, so 5.5 times 9 minus this whole term, m2 v2a, so m2 v2a, so 0.85 times 15, and then cosine of 85. Okay, so actually, yeah, cosine of 85. All right, wonderful. So now let's just throw that on into the calculator. So I'm going to do the denominator first, 5.5 times 9, and then minus 0.85 times 15, and then times cosine of 85. And then I'm going to take now the numerator, so negative 0.85 times 15 times sine of 85, and then divide it by that entire denominator. Oops, hold on one second. I'm going to re-plug that in. 0.85, negative 0.85 that is, times 15 times sine of 85, all divided by then that answer of the denominator. And now I got to do the inverse tangent of that. And we get a value of negative 14.7. Okay, so the theta here is negative 14.7 degrees. Now what does that mean? Well, anytime you get a negative angle, it's negative in reference to the positive x-axis. Okay, so what that means now is this angle here, I know the angle now. Okay, so I found the direction. So the vector here should be pointing right here. Okay, and that does make sense, right? I mean, if the bowling ball comes in and the pin gets deflected this way, there's a good chance the ball is going to get deflected that way. Okay, so again, I didn't even need to know the picture. I just can plug in all the numbers, right? And then the numbers will dictate then at the end what the picture should look like. So this is 14.7 degrees. All right, remember this is in reference to the x-axis. So now I found that, and now the only thing I'm after now is really what the heck is V1A, right? I got to find that out now. So I'm looking for my V1A value. Okay, so I'm probably going to just use this equation over here since I solved it already for V1A. I'm just going to plug in the numbers into that one. All right, and maybe let me try to do that on the bottom right over here. I'll erase this tangent stuff. All right, let's erase that tangent stuff. And let's see if I can squeeze it on in. So negative M2, which was 0.85, times V2A. V2A was 15. Okay, 15, sine of 85, all over M1, which was 5.5, times then the sine of that angle of 14.7. Now, when you do this, though, you got to make sure, well, you can plug in the negative value. That's fine. So, or you can, yeah, just leave it negative. So 14.7, you can also plug it in as a positive. It really wouldn't matter. If you plug it in as a negative here, the answer will get spit out as a negative. Honestly, it doesn't matter. I'm just going to plug it in as a positive. So 14.7, but I know its direction already, so that's why I can do that. So 14.7 degrees, that's equal to V1A. Okay, so now let's calculate it. So V1A is equal to negative 0.85, right, times, actually, I apologize, actually leave in the negative sign down here because I realized it's probably just better. Hold on one second. Instead of figuring out when you can and when you can't, just leave it in. All right, I think it might be more confusing. So V1A. Okay, so V1A will equal, let's just calculate. So negative 0.85 times 15 times sine of 85, and then divide that now by 5.5 times the sine of negative 14.7. And we get a value of about 9.1, right? So there's about 9.1, and that is meters per second. Okay, great. Okay, so that takes care of V1A. So that would be the answer now for V1A up here. Okay, so let me just erase this question mark, and now V1A is, according to this, 9.1 meters per second. So now what we have to ask ourselves is, is the collision, so letter B now says, is the collision elastic, right? Is the collision elastic? Now remember, in elastic collisions, what must be conserved? Kinetic energy, right? Kinetic energy has to be conserved. Now you can already look at the numbers and realize that this is not going to involve conservation of kinetic energy, because look, the velocity over here of the bowling ball is 9, and then after the collision, somehow it's now 9.1. So already that tells me that there's going to be more kinetic energy after the collision than there was before the collision, not even factoring in the pin. All right, so I'm not even going to do any math there. There's no need to do it. So for letter B, let me put B here. For letter B, the answer is no, it is not. Okay, since there's no conservation of kinetic energy. Letter C says linear kinetic energy is greater after the collision. So there you go. And that's exactly what we just found. Discuss how spin on the ball might be converted to linear kinetic energy in the collision. So basically, as the ball rotates, it has a certain rotational energy to it. And then as it hits the pin, right, that rotational energy, the rotation of the ball grips the pin, so to speak, and it's translated into linear energy. Anyway, guys, thanks so very much for tuning in. Please remember to subscribe. Look forward to helping you out with the next question. Take care.